Sup guys, welcome to today's show. Last time we started coding on this encryption cipher, XSC 256, and we made a lot of the utility functions and set up the project. So today we're going to start coding on the inner functions, and we are going to start with what I call the Xbox. So the Xbox is an expansion box. We go in with 128 bits and we go out with 192 bits. And it's a byte wise permutation, which means that we're just moving some bytes around. And every second byte is being moved, and every second byte is being moved and copied. So it will go to two places. And the function itself is pretty simple. It's just a lot of x at index 5 is equal to y at index 2, etc. according to a plan that I have made. So let's begin. So let's see, I think I created a empty version of this thing. So we have Sbox, Cbox. Where is our Xbox? Here it is. Alright, so what are we doing here? We are just copying the input to the output at the moment. So we can remove all this stuff. And since we are dealing with bytes, we can make a one-dimensional array of everything. So let's say we have, let's say the input is called X and the output is called Y. Simple enough. Alright, so what I'm going to do is I'm going to create two pointers. So one for X and one for Y. And I'm going to point this thing towards the input. Well, towards the address of the input. And then we will just have a lot of, let's see, we're gonna have an output as well. So we need to create, an int192 output. And Y is going to be that output. So let's see how we're going to do this in a good enough kind of way. I think I'm going to do something like this. I'm going to create an additional file. Let's call this const.c, where we are going to put all our constants. So we include the main header file, and I'm going to create a constant which I'm going to export. So this is going to be a list of indices. So let's say int 8 indices. And here I'm going to put the order that we are going to shuffle these bytes. Alright, so here we have all the indices. So let's go to the H file and define what export means. So define export. So this is an attribute with visibility. Let's see here. Is it like this? Not hidden, by the way. Visibility default. I think this is right. And let's, by the way, do the same for, we had some other, right, the RCs. Let's move them into the const. And export them too. And let's update the make file when we're at it. So we're gonna have a const.o from const.c. We're gonna run cc with some flags -c and take the input file, and then we can link it here like so. And then let's also do something like this. Define so we know that we're in the main file, and in that case so if main is defined, then we can import these things. So extern const int 64 RCs. Not sure if we can do this, perhaps. Think so. And then int 8 indices. So something like this. Now we should have access to them inside of here. Let's remove this Fibonacci stuff. Okay, so how are we going to do this? We need to create a counter. Let's say int 8n. We'll do a for loop where we set n to 0, so n is less than so this will be based on the input, and we have 16 different inputs. N plus plus. Mm, mm, mm. So what are we going to do here? First of all, we need to check if we're even or odd, because if the number is even, then we will just copy the value to one place. If it's odd, we're going to copy it to two places. So we need to have an index pointer. We'll set the index pointer to the indices. Alright, so let's check if it's even or odd. So if n mod 2, if this is 0, then it's even. So here we're dealing with the odd case. And in this case, the only thing we are going to do is we're going to take the output at index pointer and set it equal to x of n. And then we're going to increase this, so we go to the next index. Otherwise, we are going to set y at index pointer plus is equal to y at the next one, and this is equal to x of n. And I think that's it. So now we should just be able to return the output, I guess. I guess we need to dereference this. Quite good looking code, I think. So how do we test this? I want to have some input which is easier to deal with. Let's remove this main and put it at the end so we find it easy. And let's say we have an int 192. Y. And we have an int 128x. And I want to fill this x with something which is easy to deal with. So let's say we have an int 8n as a counter, and we have an int 8p, which is a pointer. So let's do a for loop where we set n to 0, p to the address of x. Actually x plus. So how many bytes is int 128? It's 16 bytes. So we add 15 to get to the last one. We go until we are done with all of them. And x plus plus and p minus minus. We'll set p equal to we set p equal to n like this. So then we should get a number which looks something like this. So 1, 2, 3, 4, etc. So let's see if that worked. So we can do show x. Something like this. Incompatible pointer type const int star I pointer is equal to the address of indices. Maybe we should not have that at sign. I mean ampersand. Assignment discards const qualifier. Doesn't matter, we're not touching that. Not sure if we can do this. Operation on IPA pointer may be undefined. What if we were to do something like this is -1. We set the pluses here instead. But we keep it like this. This did not work as I hoped. Let's see, we set n to 0. We set p to the last position of x. We set p equal to n, so it should be first 0, and then 1, and then 2. Oh, x is less than. This should be n is less than, and this should be n plus plus. N is 0. P is x plus 15. Maybe we need to do this. All right, we made a too big jump. So let's see, we have 0, And we have 1, we have 2, but we go the wrong direction. We should start here. So this should just be p is equal to x, and we should go forward instead. Little endian and stuff. Alright, so now it's 0, it's 1, it's 2, so it will be easier to see what happens. Okay, so let's try this Xbox thing. So y should be equal to the Xbox of x, and then we show y instead. So let's see if we get the same bytes, but in a different order. Let's see here. So we have the 8, the 4. We did not have an 82. It almost worked. Maybe it has to do with this undefined stuff. Let's go back to what we had. Set this to the indices, and we do plus plus here instead. So we have the E, we have A, we have C, we have 7, 4, 2, 6, 9, 1, F, 4. It works. It actually works. We are reordering the bytes and we are expanding it into 192 bits. Pretty nice, pretty nice. Okay, so one of the operations is done. The Xbox is done. Let's do the Sbox. No, wait with that. The Cbox. That's pretty easy, I think. So how does the Cbox work? As you can see, we go in with 192 bits, and we're going to compress it into 128. And how do we do that? Well, so we have, if we use the same type of variables as before, we say that x is the input and y is the output. Then we have x0, x1, x2, all the way to x23. So that's our input. And we want to produce y0, y1, y2, all the way up to y15. So that's our goal. And how we're going to do that? Well, we're going to take these x's and divide them up in groups of 3. So we will have these 3, and then x3, x4, x5, etc. And we're going to do two operations. So we're going to do x0 ANDed with x1. And that is going to be our y0. And we're going to do x1 ORed with x2. And that is going to be our y1. So as you can see here, by you doing these two operations, we are mixing these bytes. So we are obfuscating them a little bit, but we are also compressing them because we go in with 3 bytes and we go out with 2 bytes, y0, y1. And then we go to the next group and take x3 and we AND it with x4. And this is our y2. And our y3 is going to be x4 ORed with x5. And so on and so forth, all the way down to y15, which is equal to something. All right? And if you don't know what an AND operation is, well, we go bit by bit. So let's say we have, let's say x0 is equal to the binary let's say 0, 1, 1, 1. And let's say x1 is equal to 1, 1, 1, 0. So we go bit by bit and we use the following truth table. So if we have a 0 and a 0, the result is 0. If we have a 0 and a 1, it's also 0. If we have a 1 and a 0, it's also 0. But if we have a 1 and a 1, the result is a 1. And the OR operation is the opposite. So if we have a 0 or 0, it's 0. But all other combinations is 1. So it works pretty much like an if statement with the AND and the OR. And we go bit by bit. So if we're going to AND these together, we start at the right here and we check 1 and 0. So that's 0. Yeah, maybe we should do this. And then we have a 1 and a 1. That's 1. We have a 1 and a 1. That's a 1. And we have a 0 and a 1. That's a 0. So the result is 0, 1, 1, 0 in this case. And how do we do this in C? Well, we can just say, we can say y0 is equal to x0 and x1. And we can say y1 is equal to x1 or x2. And we go through all of them like this. Simple enough? All right, let's see if we can figure this out. So this is the Cbox, the compression box. So this is also byte oriented, so we'll do pretty similar like we did before. So we need to have an int 8 x and y, where x is equal to the address of the input and y is equal to the address of the output. We did it like this, didn't we? Yes. And here we used an index pointer which went through an order, but in this case we're gonna just use a counter, I guess. So let's see here. So we have 192 bits as input, that's 24 bytes. And since we are dealing with groups of 3, we will have 8 iterations. So we will do something like for n is equal to 0, it's less than 8, n plus plus. So let's see here. We still need to have some kind of thing which deals with the indices. So let's set idx to 0 as well. And what we're going to do is we want to set y of that index equal to x of that same index ANDed with x with plus plus index. So first we're going to have 0, 0, 1. And then we're going to have y1 is equal to x1 ORed with x plus plus index, so 2. So 0, 0, 1, 1, 1, 2. And the next round 2, 2, 3, 3, 3, 4. I think this is right. Yeah, I think so. And then at the end we just return the output. Pretty simple. Oh, I'm changing the wrong thing here. So let's see here. I'm going to switch these two because now we want the input to be 192 and the output to be 128. And this is the Cbox. And let's go to 24 here instead. And let's remove this annoying warning. Incompatible types 178 X. That's right. I want to change this this semi-word structure a little bit. No. Let's see here. The 192. Okay, never mind. Let's just do x.x is equal to this. So we have 0e, 0f, 0c, I think it's doing the right thing. So let's see here. Let's change these back. This goes back to 16. And let's say y is equal so we have an x which is 128. So let's run the Xbox going from 128 to 192. We expand it. And let's say we have a z. So then we take the z and we compress the y. And we show the z. And this should be changed back to x. Okay, so now it's starting to get pretty obfuscated. And what happens if we keep doing this? So if we copy this, paste it in, then we set y is equal to the Xbox of z. So we run 2 rounds. Okay, looks pretty good. So every time we run these operations, it's going to be expanded and then compressed, and at the same time become more and more encrypted every time. Pretty nice. So then we have the Sbox. And we have already a function which will go through all the different inputs. But I think this Sbox's function actually provides the wrong result. Let's remove this again and make this a y and this an x. We go through all 24. So what do we have right now? "17, 16, 15, 14, 13, blah, blah, blah." Okay, that's good. And currently the Sbox function should not alter the input. So if we were to say x is equal to the Sboxes of x, will this value change? So let's see, this is the output. Yes, it changed quite dramatically. But if I remember correctly, this did work the last time. Let's see, what does the Sbox function currently do? What if we were to just do like we have done in the other cases? So let's see, int 192, int 192, int 192 Sboxes, int 192 input. So we have an int 8 n. Int 192 output. We have a semi-word x and y. So the x is the input, so we set this equal to the semi-word pointer of the address of the input, and same in the other direction, semi-word output. And let's start by setting the output to 0. So the output at index n is equal to the Sbox of x of n. And then we return the output. Could it be this simple? Huh. Think it worked. Let's see. Let's say that if we have a 0C, we want to change it to something else. But we can't really compare it that way. Let's just say if n is equal to 5, 5. No, 5. Then we set y of n equal to the Sbox of x is f. Y is F, Z is F. Otherwise, this. I'm not sure if we can do this. Huh, pretty cool. C0 and then 09. So C0 and then we have this and then 09. It works. It actually works. The simplest solutions are often the best. Okay, so now we can actually take care of the Sbox. We should remove this. This was just a test. Okay, so this is done, but we need to do the actual Sbox function, which is going to replace this thing, which means we need to construct an Sbox, or at least a temporary one. So let's just create an empty one for now. So we're gonna have 0x0f, 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 like so. Okay, that seems to work. And then we need some function, at least a temporary function, which fills in some data inside of this. So void make Sbox. And we need to provide a pointer to this thing. Actually, no, we can use it as a global. So we need to have 3 nested loops. And then we can do Sbox of x and y, no, z and y and x is equal to what? What are we going to put here? Maybe just some counter or something. So let's do semi-word, and then we create a semi-word where we can reverse this thing. So we set x equal to z, y equal to y, and z equal to x. Expression must be a modifiable L value. Well, I guess that's it. So how do we test this thing? Well, we can just do this. So we make we make the Sbox, and then we call this as before, but we need to modify the actual Sbox function. This. So we are going to return the Sbox of input input C, I guess. Input Y, input X. Something like this, I think. Assignment of read. Oh, I made it const, didn't I? It compiles. Okay, so this is what we get. I guess it looks right. And this is a very linear Sbox. When we do this for real, we need to create a proper box which is not vulnerable to linear cryptanalysis and differential cryptanalysis. But this works fine for now. So let's run a whole round and see what happens. So instead of just calling the Sboxes, let's see, what do we start with? Let's start with an X. instead, like this. Set our y equal to the f of x. And if you remember, the f function does this. So it first runs the Xbox of the input. It takes that expanded output and runs it through the Sbox function, and then compresses it with the Cbox function and returns the output. So this is one round. So we start with x is equal to 0, 1, 2, 3, 4, etc. And after one round, we end up with this. F0, E0, D0, C. Wait a second. I'm showing the wrong thing. I should show Y here. That's better. 00 FB, 00 FE, 08 FAO2. It looks pretty obfuscated. A little too much of 0 words, but we can fix that. So let's try to run, how many rounds is there? 64 is what we need to run. Maybe it's easier if we remove the y and do x is equal to this. And now we can do a for loop, n equal to 0. And we go all the way to 64 and plus plus. And we run the same function over and over. And what we end up with is the following. Boom. Yeah, most of it has changed. I don't really like these 0 bytes though, but we'll figure them out. So what's left? We need to be able to rotate, and we need to be able to add the key. And that's pretty much it. So I think this is enough for now. I hope you liked this episode and that you learned a lot about encryption. Please don't forget to like and subscribe. And thank you for watching. Thanks for today.